get started. I know that we're not quite there, but we'll be walking. Hopefully not too many more. Okay, quick reminders. Guys, quick reminders. A1, good night. 11:59. 1 minute late, Blackboard freaks out, marks it late. It's not that big a deal. So one of the things we have not discussed is late days. I didn't want to discuss it very purposefully because I didn't want you guys to be late on the first assignment. That's not a good way to start. So I'm very nervous to offer this on the first assignment. However, going forward, starting with assignment 2 and after, we are going to have an official late day policy that will give you 3 late days, but it does not apply to assignment 1. If you were late on assignment 1, you will actually lose points for each day that you're late. And the reason is because assignment 1 is supposed to be the easy one. Like, come on, guys, this is the easy part of the semester. You're supposed to be like just kind of nailing this, and it's best to get it on time. But if you absolutely are late, if it's a few minutes late or whatever, nobody's going to care. We're not hard asses. But that's going to be our late policy going forward. Is we have several late days spread over the semester, but not for assignment 1. Other things, I have office hours of 2 to 3 p.m. today. They're in Malone. I should write this. Malone 313. I really only have 1 hour because unfortunately I have a call. So if you have like a really big complicated question or something, first of all, there are TA office hours. There's going to be a review session tomorrow. You can write email to me or send me a note on Piazza specifically to me, and I'll try to figure out how to make some more time for you. But I hope nobody's going to come in and say, I have a question about part 2 of the assignment. How do I get started? So please don't do that. Like, if you have something you want to ask me. That's fine. The Golang review session, just a reminder, I told you about this last time, is tomorrow, 5 to 6 p.m. in Bloomberg 178. Yes?
So are there going to be notes or anything posted regarding that review session?
From
the review session?
Good question. So I'll talk to Alicia. If he has slides, I'll try to get him to post them. If anyone wants to volunteer to take notes, that would be awesome. Was that a hand raised to volunteer? Stretch when I ask questions like that. We don't have any official plan. I mean, the idea is like, if there are slides, I'll try to post them. I don't know what Alicia's plan, but I'm not going to take notes. So let's see what happens. But please do go. Take notes. Share your notes. I don't have a problem if you share notes. It's okay. Yes?
Are there any submission specifications that you want for the assignments? Like RAID, zip, file?
I don't care as long as it's a format. So we had some people, I think I may have said this already a few years ago, who used a pirated copy of Visual C++ 2012, and this was like in 2014, to do their assignment, maybe 2009, whatever. So these people did that. So don't do anything like we can't untar or unzip, but I don't really care whether it's a zip file or a tar file. I would assume it's one file. There should be either, ideally, a makefile or build instructions that will work across platforms. I haven't been hyper-specific about this if it's not obvious how you build this thing. Or like a little readme.txt file that says, like, here is the command. Unless it's totally obvious, put that instruction in. I gave you, the idea of this is to make our grading easy, so hopefully your stuff will actually compile and correspond with the command line inputs that we expect, and try to make those pretty unambiguous. So hopefully the idea is we're going to write a script, and we're going to blast through a whole lot of assignments, and then we're going to look at code. So if your code does not properly implement the expected interface, that will be a problem. So you check carefully what it does. Okay. All right, good. So that's housekeeping. Any other housekeeping kind of questions about the assignment? No. Okay. Yes.
What should we do about multiples of blanks?
Good. You should, I think, try to output the one you are most confident in, which probably will be the shortest one, is my guess. We're not going to use keys that are likely to trip and give, the wrong, weirdly repetitive keys or anything like that. So, and we're going to try across a lot of keys. So if you trip and fall on a few of them, it's fine, as long as you get it fairly well right on most. Even if you give it doubling, it's not going to be fatal. Like, it tells us you did the right thing, but maybe it's just is triggered on the wrong key. So, yeah.
A couple of my examples, I did something to try to resolve ambiguity when there were multiples of things, but there was one example where it failed and it did a doubling, and when it spat out the key was correct, but double, is that pretty close?
That's pretty close. We're gonna try to come up with examples that don't trigger that case for grading. But if you do, fine, whatever, like, it's not gonna make me sad. A double key is a perfectly fine decryption key, so I don't care, like, it's okay. It decrypts the text, I'm okay with it. Good, any other questions? Guys, don't stress about this. Like, it should work for some text, it won't work for other text. We'll look at your code, we'll know if you're doing the right thing. It's gonna be okay on this assignment. It's not intended to be a super killer. I hope it hasn't been. Maybe it has. Maybe Go has made it awful.
Yes.
But like, you learned everything there is to know to get into Go, so you're on your way. Okay, good. Anything going on in the world today I should know about? Yes.
The Apple just released their new technology, which is Face ID,
Yes.
which takes away encryption with your fingerprint. Supposedly, it's something of the order of 1,000 times more secure, or something like that.
Okay, what does that mean 1,000 times? How do you measure the security of a face sensor?
And what they said was that Touch ID could fail 1 in 500,000 cases, while Face ID was 1 in a million.
Okay. So leaving aside the marketing speak, what is fail? What's the definition of failure?
Collision.
Collision. Okay, fine. Collision. So what does it mean? So basically, what we're saying is that it might be that you share a fingerprint with some other person out of a collection of 50,000 some odd people or whatever. So if we get 50,000 people together, probably there'll be a collision. That's basically what you're saying. And then the faces are so much more unique that probably we're not going to get a collision unless we get like 1 million people together. Is that the right metric for measuring the security of a biometric token? Why not? Go ahead.
I mean, it's also how easily it can be tricked.
Good. Okay, so I could definitely come up with a fingerprint sensor that like literally has this property that if 50,000 honest people come along and put their fingerprints on it, it does not open. Maybe once, maybe that's collision after 50,000. But this thing could have a total bug in it. That means if somebody is trying to come up with a matching fingerprint, like they could just open this thing right up. So this is a little bit of a weird metric, this idea of facial collisions. Nonetheless, we'll see. So really, this is a big difference between adversarial collisions and random collisions. And actually, this is going to come up all the time in crypto, right? Like you take a checksum, a non-cryptographic checksum algorithm, pretty good one, and you throw lots of inputs into it. Is it going to produce collisions if it's a good one, has a long output space, and they're random inputs? You could probably say this thing's pretty collision resistant. It's not producing the same output for lots of millions of different inputs. I get different outputs. But then you look at the checksum algorithm, you figure out how the code works, and you put some intelligence into it. Wow, now I can by choosing 2 specific inputs, I can easily find 2 that will produce the same checksum. So this idea of adversarial collisions versus non-adversarial collisions is actually a big place where non-security people trip up. Now, Apple has really good security people, so we'll find out how secure it is over time. Does anyone know how the Touch ID sensor was defeated right after it came out? There was a presentation at CCC. Yeah.
Yes, I think it was possible if you just take a picture of the fingerprint and put it on, let's say, some sculpture or something with a hand, and just put it on the sensor.
Yeah.
And it was quite easy.
So the way I remember even one version of this is they took a piece of Scotch tape, they took some pencil filings, like magnetic graph, I don't know what the heck it was, and they sprinkled this all over the phone. They peeled off and they got basically a copy of your fingerprint, and they pressed that up against the sensor. And it turns out the Touch ID sensor is really just like a very high resolution capacitive sensor that basically takes a picture of what you press, and that was enough to open the phone, at least back then. Yeah.
If you try to upgrade it to look on the second layer of the finger.
Yes, so now it tries to look deeper in.
Yeah, right.
Yeah, so these are the kinds of things you can do to try to make this harder. So this new sensor is a 3D infrared sensor combined with a camera, combined with neural nets, like it's all sorts of stuff. We'll see how good it is at sending off.
Do you think it's possible to just do a 3D printing with your face already?
So apparently Apple tried to hire all these Hollywood mask makers.
Even with a 3D printer?
Well, who knows what they used. So we'll see. I mean, Apple tried some stuff, and I'm sure they, there will be people who attack this, and will find ways to make it broken. But for now, like they're trying the obvious stuff. Yeah.
One concern that I have that is going to be coming up is the issue of privacy. Because if you're using your fingerprint on your phone, that's one thing. Because on your phone with your fingerprint, and you're not different with
You
your
can
face.
chop that finger off and you're done with it. You can get it over, right? You only have 10 fingerprints. Go ahead. Yes. No, continue. I'm sorry.
Right, yeah. It's only 10 fingerprints, so yeah. But, well, I mean, even one fingerprint's enough to like identify, say, a law enforcement database or like a matter of privacy, that's one thing. But then using the face and then also requiring the use of the camera in order to come in. So like I know a number of people who refuse to use cameras on their phone out of a privacy concern.
Okay.
And so I'm saying like, does that like required opt-in as such
So,
become
so,
an issue?
so this is actually a good question. So let's say privacy is a real concern, that your biometric is going to be inside this phone, and you don't want Apple or anyone who breaks into Apple to steal it. What has Apple done to try to fix this problem?
So Apple has in its hardware somehow some components that are strictly independent of Apple, so those like privacy issues. For example, the fingerprint or your face or any other keys are just on the device. Apple does not have any access to it.
Right. I mean, at least they say they don't, right? So I mean, they make the phone, so we
Yeah,
have
well,
to trust
that's
them.
self-visibility.
So the basic idea is if you break open a modern iPhone, you're going to find two processors in there. One is called, obviously, the application CPU, and that's what runs all your software. But there's a second processor in there that's called the SEP. And this stands for Secure Enclave Processor. It's an entirely different CPU that has its own secure storage. Supposedly, it's got some tamper-resistant stuff, like a shield on top of it, makes it hard to crack open. And this thing, right now, on your existing iPhone, connects directly to the fingerprint sensor. So when you program it, the fingerprint lives inside of the storage here on the SEP and never goes to the main CPU, which means if you download something like horribly malicious app and this whole CPU, the kernel is exploited and you're totally busted on the CPU, still your fingerprint template should stay secure inside of this separate processor. And that's their solution to this privacy problem. Now, obviously, if this processor has a bug and you can jump from the CPU into this processor, then things are really horribly broken. But this seems to be the way that they've gone. And again, they're going to repeat this with the face thing. So what that implies, it's a little unclear what that's going to mean, is that they're going to have some kind of sensor, which is their infrared sensor, plus their front camera is going to have a path directly into the SEP. I'm not sure how any of this is going to work, and I don't know. So it's not clear if they're actually going to rig the cameras directly to connect to this or what they're going to do, because if they don't do that, then every time you log in, then you're going to have your data going first through this CPU, and it seems to be a problem. But again, none of this stuff is out yet. We can't look at it. We will look at it soon. Yes?
And so, in terms of the face being an identifying thing, there was the paper a few days ago which claimed to have like a sexual orientation classifier with like 90% accuracy using only facial features extracted, which are funny methodological features you could raise. But the question is like, what kinds of things did people learn about you by accessing your face?
Well, the good news is we post our face all over the place anyway. So for the most part, we're probably not hurting ourselves too much by using a face. But there are people who will be really paranoid about this. Okay, so any other news unrelated to Apple? Because Apple devours news. When Apple comes, it does something. It like ruins everything. What else? Yes.
Newborn is a vulnerability apparently that can allow an attacker to access your phone via Bluetooth and then spread it to other phones that have their Bluetooth on.
Good. So if you leave your Bluetooth on, then somebody can remotely attack your phone. How do they remotely attack your phone? Okay. Anyone guess how they might remotely attack the phone? Yes.
The article briefly said man in the middle attack.
Oh, interesting. Okay, so yeah, it seems like there's a problem with the crypto and Bluetooth. Yes. And also, I think there's even a remote code execution vulnerability where somebody can actually like exploit a piece of the Bluetooth drivers or stack somewhere in there. I'm guessing, I don't know. And they can actually get code running on your phone, even if your phone is literally just listening for devices to connect to, meaning you've left your Bluetooth on. So what's the ultimate scariness of that? Well, somebody could build a Bluetooth worm that would hop from your phone to other nearby devices and then replicate itself to any other device. And so you could end up with a lot of devices being infected very quickly. It hasn't happened, or it has happened with Nokia in the past, but it'll be more interesting now that we have all these Bluetooth devices to see what happens. Yeah.
I think the scary thing is when it's on cars and computers and things that.
Yes, things that actually go. So yeah, these kind of vectors, we don't know. Right now we think Bluetooth's a short range thing. You can't attack most things. But if I can use your phone as a stepping stone to get to a device that I do care about, then these kind of threats are actually a big deal. So hopefully they'll patch that, which means that most Android phones will never get patched. Okay. Moving on. So today we're going to do a little bit of review, a couple of things that we talked about last time, including drawing a proper diagram of a high-speed network, because I can tell that was not going very well last time. I think I had wires going all over wires, so we're going to try this one more time. Quick reminders. Okay, so skipping past all this stuff. What we were talking about was, last time we started talking about block ciphers. Somebody tell me, what is a block cipher? What does it do? Forget about the math stuff. Like, what is its purpose? What does it take in? What does it spit out? Yes.
Yeah, we have information, we cut it into pieces,
Pieces.
and then we encrypt every piece.
Good.
Let's
Okay.
say block.
So these pieces we call blocks, and they're just sequences of bits of a fixed size. And what comes out of that cipher? Well, I'm sorry. We have information. One of the inputs to one of the algorithms is these blocks of information, plain text. And we also feed into this block cipher another input. Remember what that was? Good. Okay, so we have a key and a plain text input goes into an algorithm which I called what? Okay, well, let's say we're talking about block ciphers generically. So I want to cover DES, AES, skip that. Okay, well,
By hash, I mean something that mixes it up and scrambles it.
well, you're getting too detailed. You're getting too deep into it. So remember, we have two algorithms in a block cipher. What were the name of those two algorithms? Good, or more specifically, N-cipher, D-cipher, if you want to get a little bit hairy about the actual terminology. So N-cipher, good, D-cipher. All right, some people write this as, e to the -1. I hate that, so we'll just call it N-cipher and D-cipher. And the profile was we get a block of plain text in. This was a block of bits. We feed a key in. I like to put that on the side. D-cipher we spit out a ciphertext. Similarly, D-cipher takes in a ciphertext and spits out a plain text. It also takes in, hopefully, the same key. And the property that we want is if we put in a given key into both of these algorithms, we stick in any plain text that's in its allowed plain text space. We encipher that, take the resulting ciphertext block, feed that into the D-cipher, we get back to plain text. That's called correctness. We need that to be the case, otherwise we don't have a good block cipher, because the first time we try to decipher something, we're going to get junk. Not very useful. So that's one thing that we want out of this block cipher. Now another thing we want out of this block cipher, obviously, is that the ciphertext is somehow not obvious. You can't easily, without knowing the key, go from the ciphertext back to this plain text. And I kind of talked about what that means, but I think there was a little bit of confusion, so I want to go over a couple of things. So this block cipher, obviously, when you implement one of these things, you implement them, you're going to write some algorithm for doing this. But fundamentally, this is a pair of functions, right? So these are functions. What's the definition of a function, the mathematical definition of a function? Or just the intuitive one? We get confused in computer science because someone decided to name algorithms or subroutines, named them functions when we started writing C, so we get confused between algorithms and functions. Somebody was raising their hand. Yes?
Like maps inputs to outputs.
Good, it maps inputs to outputs. That's all it is, a mathematical abstraction that maps inputs to outputs. So if this is a function, it has the interesting property that this is, a finite set of inputs, because it's just a block of a certain number of bits, and a finite number of outputs. In fact, they happen to be the same. We stated that was one of the properties, same size, that is. So, okay, what are the inputs called? What do we call them when we have a function? What is the set of inputs to a function called? More generally. Yeah. Domain, good. So a function maps some domain, that's my D, not an O, to what?
Range.
Range, good. And if these are finite sets, that's what a function does. Now, let's talk about algorithms. Tell me how you implement a function with a finite domain, finite range. How would you give me a generic approach to implementing any function that has a finite domain and a finite range? Algorithm. Yes. Did you raise your hand?
Yeah, you just make like a big list.
Good. You make a gigantic table that has every possible input listed there and every possible output. Because functions, remember, these are just mappings. The algorithm, there are lots of algorithms you can use to compute a specific function. The algorithm doesn't always matter. I'm talking about this as a mathematical object. If we have a finite domain and a finite range, we can always take the dumbest possible implementation of it, and it can just basically think of it as a gigantic mapping, a gigantic hard-coded table from inputs to outputs. And the reason I say this is when we talk about these functions, we're talking about something that is deterministic. These are not like randomized algorithms. These are mappings. They're specific set relationships between input and output. That's all they are, okay? Now, all right, so now that I've said that, I want to talk about the implementation of something like a block cipher. Let's talk about AES. How big is the input space, meaning the domain? Let's forget about the key. Just forget about the key for the moment. just the plain text. How big would that table be for one particular instance, and I've set it up with just one fixed key of AES? Does anyone remember how big AES's block size was? Okay. 128. Okay, AES takes 128 bit strings as its plain text. Now, forgetting about the key, just assuming we have one key, how big is that gigantic table that you said I should build? How many entries does it have? 2 to the 128. Good. So we have a table. This is the naive implementation of AES of size 2 to the 128 entries. And each entry is how many bits long? How big is the output for AES?
128 bits.
Times 2, times 128 bits. Okay, now let's do a little binary arithmetic just so we do this and we all know we're on the same page. I want somebody in here who's not being too ambitious to tell me, I'm going to give you some binary powers of 2, and I want you to give me English language or decimalized expressions of those. Okay, 2 to the 8. How big is that? How many possible values can you stick in 2 to the 8 size register? Or what is 2 to the 8? 256. Okay, simple. 2 to the 16, quickly. 65,536. Good. 2 to the 32, approximately.
2.3 million,
4.3 billion.
Let's go with 4, approximately 4 billion. I'm good with approximate here. Okay, 2 to the 32. Can somebody do this for a larger power of 2, just off the top of your head? 2 to the 40. People are like multiplying in their head. This is not good. Okay, I happen to know this because when I was in grad school, we were trying to implement something at brute force, a 40-bit key. And so I can tell you off the top of my head that 40 bits is approximately 1.1 trillion. Okay, so we're getting bigger fast. I know you guys know this, but I want you to feel it. Okay, so let's stop. 2 to the 40 is really the biggest I can do from the top of my head. Approximately, and I'm just even going to get rid of the 0.1, and I'm just going to say approximately a trillion. Okay, let's go much bigger. 2 to the 80. Nobody can do 2 to the 80? Yes.
Is 1 trillion times 1 trillion.
It's a trillion. Good. Okay, we're getting bigger. Okay, so 2 to the 80. 1 trillion. All right, we're going to keep going on this approach, and we're going to go to 2 to the 120, which is a trillion. Okay, we get the point. These things get big fast. Can somebody tell me how many stars there are in the universe? Can anybody quickly Google? 10 to the what?
I think 10 to the 56-ish.
Good, which works out in binary 2, I don't know, multiply by 3, so like 2 to the 150 or 2 to the 160 or something like that. So we're getting, maybe I'm just approximating that, but we're getting into the neighborhood of numbers that are insane. In fact, once you get up to about 2 to the 256, we're talking about like number of atoms in the entire universe range. I just want people to feel this. I know you guys can work this out yourselves. It's not a big deal. I want you to feel this because in a lot of classes, I get people saying stuff like, well, couldn't you brute force AES? And I want you to see these numbers and internalize them because I don't want to hear people saying stuff like that because AES has a 128-bit key, which means it's many trillion possible values. You're not going to do this. And the reason you're not going to do this is because when we start getting into things like the number of keys is equal to the number of stars in the universe or the number of atoms in the galaxy, there is no computer that you can build, whether it's parallelized or serial, that is going to do anything more than just dent the edge of these numbers. I want you to just feel why they're big. Now let's get back to this function stuff I was talking about. Okay, so we talked about how for a finite domain, finite range function like AES, we could always implement AES as a gigantic lookup table, right? Every input, we'd have the output for a given key. We're still not worrying about the key yet because that's even bigger. All right, where do we run into problems with that approach for implementing AES?
Your memory requirements would be huge.
Good, so we're not going to go out to Best Buy and pick up a whole bunch of like USB keys to store this thing. It's not going to work. Okay, but let's leave aside the memory. Let's say I go out and I find somehow in the planet enough memory, hard disks, whatever, to build a table of size 2 to the 128. Forget how I did it. I did it. What's the second problem we're going to run into? Lookup time. Good. Why?
No fat cache efficiency?
Okay, well, I mean, you know, let's think about it in a different way. Think if we have a pile now of USB sticks that is the size of, like, the solar system, it's going to take a while for things to look up. Okay, so we tend to think of lookups as instantaneous, but of course there is a model for computation that a very famous cryptographer once developed back in the 1930s that makes the cost of lookups very obvious. And what is that model? If you remember your, boring CS theory, what is the machine, the universal kind of machine that we like to think about in computer science that makes lookup costs very obvious? Somebody say it. Good. And in Turing machines, why are lookup costs so obvious? Remind me, what does the storage look like in a Turing machine? It's a giant tape, so every time you move down that tape, you spend computation time. So that makes lookups incredibly obvious. So what we're saying now is to implement AES using this naive lookup table algorithm, we're going to have to write a tape that is 2 to the 128 at least, or 2 to the 128 times 128 symbols or bits long, whatever we're going to do. And so just getting to the place we're going to look up is going to take us basically some vast number of time steps. So we're not going to be implementing AES this way. I just wanted to point this stuff out because it kind of illustrates a couple of things. First of all, just knowing how big these things are is useful, but it also illustrates something else. And I mentioned a couple of things last time. One of them is I mentioned this idea of a random function. I think I said random permutation specifically. Can somebody tell me, now a random permutation, I'm not talking about an algorithm, I'm still talking about a function. So we're just talking about a particular mapping, which means it's not a randomized algorithm. That's different. What is a random permutation? What's the definition of that? Shoot.
Equivalent of the all permutation set.
All possible permutations. And we talked about there are a lot of possible permutations. There are even more possible functions. Once you fix a particular domain and range size, then you're basically talking about a huge number of these things. So a random permutation means we calculate all possible random permutations over a specific domain and specific range. We enumerate them, and we pick one of those at random. And the number of those is almost as big as, it's even bigger than the number of possible, this is just one table, but the number of possible tables you could build is, exponentially larger than that. So we do not implement things using even random permutations because the size of the description of a random permutation would itself be vast. So instead, when we build something like a block cipher, we build it out of something smaller. How big is AES? How big is the code for AES? Has anyone ever seen it?
Too big.
What's that?
It's not too big.
It's not too big. It's like, you could probably fit it in 10K tops. If you're really compact, maybe you can even squeeze it down to a couple of K of source code or something smaller if you're going to actually compile it. So great. So AES is tiny. And yet AES implements not just one of these vast tables. It implements one for each key. It implements a different possible permutation. So somehow we've squeezed all of that down into a relatively tiny little algorithm, which is in no way going to be confused for the full family of all possible permutations. Or if we sample one key for AES, we're not going to get a random permutation. We're going to get one of AES's specific permutations. So, and this gets to the security of block ciphers. What does it mean for a block cipher to be secure? What does it mean? Does anyone remember? I kind of briefly mentioned it last time. Okay, let me try to spell this out as clearly as I can. So, to a computationally limited, and I'll get into the detail of what that means maybe later, attacker. Hopefully you don't need that. A single randomly selected permutation from a block cipher, meaning one key of a block cipher, should be what? Should be what? The end of the sentence is going to be a randomly selected permutation from the family of all possible permutations, but there's a word on it. indistinguishable. Meaning, if I run an experiment with this attacker, that's as much of it, right? From a random, sorry about my handwriting, permutation. Okay, hopefully that's readable. So the gist here is that this little tiny thing that I've made, this block cipher algorithm, if I select a random key from it, and I let you, the attacker, send me inputs without telling you the key, you can send me inputs and I'll give you back the AES encipherment of those inputs. Send me more inputs. I'll send you back the AES encipherment. Okay, that's one experiment. Now the other experiment is I select magically from the family of all possible permutations with this domain and range, I select one of them. No way I could actually do this in polynomial time. I'll do it. And I'll let you send me inputs, and I'll send you back outputs. And you'll see, and at the end of this, your goal is to tell me, were you playing experiment 1 with AES, or are you playing experiment 2 with this magical random permutation? And if you're computationally limited, you should not be able to win that experiment with much more than basically the probability of random guessing. Okay, so this is the kind of mathematical definition. We'll get more into why this is so important later. But I want to basically put it a different way. What do the outputs, if I sample a random permutation, and I give you back, let you query me on inputs of your choice, and I give you back the responses to a human being, overwhelmingly, what are those outputs going to look like? Are they likely to be like structured looking? Are they likely to be related to the inputs you gave me when you query me? No. With all probability, they're going to be a bunch of random looking noise because I'm sampling from the space of all possible permutations. So when I say a block cipher is indistinguishable from that thing, that basically is as random as you can get when you're locked down into this particular profile, I'm saying that the outputs of a block cipher look really random, look really unrelated to the inputs that you're sending to the block cipher. Okay, last question. If you were not computationally limited, if you could run for as long as you wanted, and I ran this experiment where I gave you AES with a random key, and you could query it, you wouldn't know the key, but you could query it, or I was over here, and I have a random permutation, and you can query it, would you be able to tell the difference? Would you be able to win that experiment and distinguish the two? How would you do it? Think about it. You can run for as long as you want. You are an unbounded adversary. What would your strategy be to tell the difference between AES with some random key that you don't know and the set of all random permutations? Now, I told you guys you couldn't brute force anything, but I've just said you can be an unbounded adversary now, so I'm giving you permission. Yes?
Go through the set of all random permutations.
Oh, now you're just doing it. You're doing it too hard, but you're close. You're close. What would you could do that, sure, fine. But there's a slightly easier strategy. I guess you're an unbounded adversary. Do whatever you want. But what if you try every AES key? So you ask me to encipher a bunch of values, maybe 1,000 of them. Okay? And then you try every single AES key. This takes you a long time, but you're an unbounded adversary. And you find if there's any AES key which causes those 1,000 values you asked me to all encipher to the result that I gave you back. Okay? If I'm in the experiment where I'm actually using AES, then that's probably the result you'd expect. You'd find some AES key that would match what I'm giving you back. If I'm over here in the random permutation experiment, well, trust me, the probability that in a random permutation you're going to get back results that exactly match one of the permutations in AES is actually very, very small. So even if you give me a few tests, probably one of them is not going to satisfy. So this is the point. So we have to make it a computationally limited attacker, and the reason is we can't let him brute force AES. If you can brute force AES, you can always distinguish these things from random, and they will never be secure. So we are talking about somebody who can only run for a reasonable number of time steps, which is fine because AES has 2 to the 128 possible keys in its lowest setting, and we've already specified that nobody's going to build a computer that can brute force through too many of those. Whew. All right, good. So another thing we talked about last time, actually forget this, the thing that I did not do a great job at drawing was how you can build block ciphers. Now, last thing is we talked about pseudo-random permutations. Another thing we could use is something like a pseudo-random function. And a pseudo-random function is exactly like a pseudo-random permutation, except that it's, indistinguishable from a random function. I have an actual picture I wanted to use here. Okay, so let's say that we wanted to build a block cipher, and we have a function f that is a pseudo-random function. Don't even worry about what that means. Just means that anything that goes into it with a key is going to come out very, very scrambled and very unrelated to its input. Let's see if I can draw this in a slightly less awful way. Okay, so f is our function. Now I'm talking here about one specific way to build a block cipher. Not every block cipher needs this. Okay, we take our right input and we XOR that. We have an intermediate value here. So what this is going to do is we're going to take L unchanged, and we're going to have R prime, which is the XOR of this right input, XORed with the output of this F function. Okay, and now we can do this again. Let's see if I can draw this properly. Except this time we're going to do it on this side, we're going to put the XOR. And on this side, we're going to have our F function. Okay, so this right R prime is going to go into F. It's going to be XORed with L. And that's going to result in L prime. And we're just going to take R prime straight down. Okay? Intuitively, all you need to see is that if F is a function that takes in an input, and I haven't added a key, but let's add two keys, so K1 and K2. An input that if it takes in an input, plain text, and a key, and it produces an output that is pseudo-random, meaning highly unrelated to the input, then by constructing something like this, well, intuitively, what we've done here is we've XORed the output of something that's indistinguishable from random with the left input. And when we looked at the one-time pad, if this really were random data, then we know that would be in cipher. It's indistinguishable from random, so we'll hope it's pretty good. And then we're doing the same thing to the left side. Similarly, what we should observe is that you can always go backwards. You can invert this. Yes?
Why do we have two keys?
Because there are cases where if you don't use two keys, this actually breaks down. So I don't want to get into it. So there are cases where you can have collisions. So by using two keys, you get two independent functions. And that just happens to work a little bit better than if you have one. There are ways to turn a single key into multiple keys. I'm just trying to make life easy for now. So what happens here is if we want to invert, we can take L prime, we go up. All right, sorry, we take R prime, we go up, and we feed this into F. We take the output of that, and we XOR it with L prime. That gets us back to L. Similarly, we take L, this that we've just recovered, we feed it into F. We XOR this with R prime, and we get back R. And you can stack these. This is basically one round of what's called a Feistel network construction. And the only reason this is interesting, you should know about this today, is that this Feistel network construction happens to be the way that DES, the data encryption standard, was built. It's how they ensured that you would always get a permutation from DES. It's used in other ciphers too. And the only thing I want to point out is that sometimes the Feistel network can be unbalanced. Sometimes you can have something like this, where you have like 2 bits and 54 bits on the right side. And you can actually do stuff like that. You have to do more rounds, but there are ciphers that do this. You can always build a permutation out of a function f that's pseudo-random by using this Feistel network structure, and that's why it's so useful. Okay? I also talked about AES, and we're not going to worry too much about the structure of that. You should just know that it is also itself a block cipher, which means it must meet the definition that I put up there. Good. All right. So the last thing I want to get to before we move on to actual new stuff is we started talking about how to use these block ciphers. We have a block cipher like AES or DES. We have a bunch of data. We want to encipher it. The obvious way to do this, that everybody tends to do when they're first making mistakes, is they chop the data up into 128-bit strings. They feed it in. They pick a key. They feed this data into the block cipher, and they get a bunch of outputs. And the outputs look like this. And that tells us something. We leak something about the underlying patterns of the data. If every single one of these inputs is different, probably we're okay. But if there's a repeated pattern of inputs, we're going to get repeated patterns of outputs. And we also talked about how this actually shows up in real files, like the Tux Penguin And I think at the very end of class, I was showing you guys an actual executable file that we had seen that was encrypted using ECB mode, which led to very obvious patterns that we were able to use to actually detect segment breaks in an executable file. So this can actually be useful and can leak stuff, limited stuff, but it can leak stuff. Okay, there's another problem with using block ciphers in their most naive form. And the problem is that because these things, block ciphers, are deterministic algorithms, they have some security weaknesses. Let's say that I wanted to play a game of poker with you. So I have how many cards? 52. I always get confused. There's jokers and stuff. I don't know. I don't know how to play poker. So I have 52 cards, and I represent those as the numbers from 0 to 51. And I encipher those all using a block cipher with a key that I've chosen. Okay? And now, later on in the game, I'm going to give you the encipherment of my hand of cards. You've already seen the encipherment of those 52 cards. And now I show you, here's my hand, but I've enciphered each card using the same key. What's the problem? What might happen there? Why is this not a good way to play poker? I've given you the encryption of numbers 0 through 51. So far, this should just be a bunch of garbage to you. But now I repeat, give you the encipherment of my specific hands in my card.
With
Yes.
a set key, you'd have a one-to-one correlation between your plain text and your ciphertext.
Good.
So I should be able to very easily figure out what you've got in your hand.
Exactly. There are only 52 cards. So yeah, the encipherment works really well. It turns the number 0 into blah, 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 blah. But then the next time you see somebody hand you the card number 0, it's still going to be that exact same blah, 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 blah. Okay, and this actually shows up in real protocols in all sorts of ugly ways. So here's one example. Let me see if I have a good one. So back in the day, there were a lot of video games that actually connected. They were like some of these like RPG type games or FPS games. And they would send a message to a server every time you did something or every time something happened to you. And those messages in the olden days, some of them were encrypted using ECB mode, which is using the block cipher in its raw form to encrypt the message, what we just talked about. Okay, the problem was that sooner or later people realized that, yeah, the messages were encrypted. But every time a monster was about to attack you, you would see exactly the same message. It was enciphered. It was a bunch of garbage, but it was the same bunch of garbage. So they built tools to anticipate those messages coming in, to filter them out, to have automated systems that could see them coming in and take actions and so on. So there was encryption here, but it wasn't good encryption because the ciphertext, after enough experience, could be correlated to what it meant. Not very good encryption. So these things actually show up and they become big problems. One of the things that people realized, and this is going back to the 1980s, was encryption that is vulnerable to these kind of attacks is not good encryption. And so you have to do something. You need an encryption property that is stronger, that works even when you have small message spaces. In fact, the example that the researchers, Goldwasser and Macaulay, came up with was playing poker. Like, poker sucks because there are only 52 cards. You don't get a lot of actual protection from that. So what they tried to do was come up with a more secure definition for what an actual encryption scheme should give you. And informally, what they came up with was the following idea. They said, in English, an encryption scheme is secure if an adversary who sees the ciphertext learns about as much as an adversary who never sees the ciphertext at all. In other words, if I dig a buried cable and I send my messages over that, or if I send them over Wi-Fi encrypted, you should get about the same amount of information. About. I said about. You might learn some stuff, like the length of the message, but you shouldn't learn what I've said. And they gave a name to this thing. They called it semantic security. And it's kind of the table stakes. It's the entry-level encryption property that any decent encryption scheme should use. And they even went farther. And they said, okay, let's make this just a little bit stronger, because they were thinking about public key encryption, which we'll get to. And they said, let's even make this stronger. Let's say this property of encryption should hold, even if the adversary can ask me to encrypt plain text of their choice. And this is actually a big deal. Like, a lot of encryption systems have been secure up until somebody convinced the encryption person to encrypt a plain text. This happened in World War II and all throughout history. That fall apart. The minute you can get somebody to encrypt a message of your choice, many of these systems fall apart. So they said, not only does the encryption have to be basically as good as not seeing the ciphertext at all, but it should hold even if the adversary can ask me to encrypt all the messages that they choose. Okay. So let's think about our poker game, right? So maybe in our poker game, I show you my encrypted hand. I'm using the block cipher to encrypt to a cipher. But now I'm going to let you say, okay, by the way, I want you to encrypt the number 5, and the number 4, and the number 3, and a jack, and a heart, whatever. And now I give you back the ciphertext. I basically told you what my hand is, because now you know the encipherment. So this is a big, big deal. So it turns out that to try to express this English language text as a mathematical useful definition is really, really hard. It involves predicate functions and enumerating over all of them, and it sucks. Nobody wanted to use this definition. But they did come up with a weirder looking definition that turns out to actually be really hard. And it's one of the first game-based experiments that we use in crypto. Okay, so I'm going to show you what it looks like. Let's start, no, let's not start with that. So, okay, so let's imagine that we have a couple of people. So we have a person, a specialized person, we're going to call a challenger. And this challenger is going to play a game with another person who is called an adversary. Of course, the adversary is the person we really care about. Okay? So what is this game going to look like? How are we going to structure a game? Well, we're going to do the following. Let's say we just want to encode the statement, if I give you a ciphertext, you should not be able to decrypt it. How do I turn that into a game with a win condition that we can talk about an adversary win? Okay, so the challenger, you can do this as a 2-move game. The challenger will pick a key K randomly, will encrypt under K a message, and what does it mean for the adversary to win this?
They give the message back.
Good. Okay, so this was the earliest definition, kind of informal definition for security. This is what people used to think security for an encryption scheme meant. The adversary would win if given a ciphertext, the encryption of some message, they could give back the whole message. And this was it. So adversary wins. And so basically this guy says, you know, so I've chosen a message here. Let's call this M prime. Does M equal M prime? And if yes, wins if M equals M prime. So that's the game encoded as an experiment and as a win condition. Why does this not make a particularly good definition? Before I get to semantic security, I just want to ask, intuitively, can you think of something, some kind of thing that could go wrong with an encryption scheme that would be really bad for most encryption schemes, but would not allow an attacker to actually win this? Yes?
If somehow the attacker were able to say tell the challenger what message to send, then they could get the message back, but wouldn't have broken the encryption.
Okay, so you're saying that, so you're pointing out something, which is what message is going to be encrypted, right? Is it going to be a random message? Is it going to be a meaningful message? What if there are only 2 possible messages in a real encryption scheme, like, or 52 possible messages? Like, where are we picking this message? Is it like a long random message or a short one? So there are questions there we haven't really resolved. Okay, so what is the message space? Good question. Another question. Let's say we have an encryption scheme where the attacker has a strategy. The adversary and attacker are synonymous. Where the adversary can always decrypt the first half of the message, but doesn't get the second half. I just made it up. Let's say we built that encryption scheme. Is that a secure encryption scheme? Would you want to go deploy that to store Equifax's data? No, not a good encryption scheme. We agree. Would that scheme satisfy this definition? Yeah, why not, right? This definition says basically the adversary only wins if they can decrypt the entire message. So an adversary who can decrypt half the message, you know, he doesn't get any credit for that, even though in practice that sucks. We don't want an encryption scheme that has that kind of weakness. So this kind of early intuitive definition is no good. Okay, so we have to do 2 things. First, we have to solve your problem, which is where do we get this challenge message, the message we're going to encrypt and have the adversary decrypt? And we have to be a little bit more specific about what it is that it means to win. And the way that Goldwasser and Macaulay, 2 researchers from MIT, came up with this, they came up with the following idea. Okay, I'm going to move this up a little just because it's kind of not enough room to draw here. Okay, so our adversary and our challenger. So they added another phase. There's more stuff. I'm going to keep updating this diagram as we go, but for now I'm just going to add one more message. So in the beginning of the game, and this is to address your problem, they said the adversary actually gets to pick the message space. What are they going to pick? I mean, we can't have them pick M because if they pick one M, there's nothing for them to guess, right? But let's say we can have them pick from whence the message that's going to be encrypted will be drawn. What is the smallest possible message space that's not just going to be trivial, like not one message? What is the smallest possible message space? 2. Good. And so they get to pick those messages themselves, and they can pick any message they want. It can be attack Pearl Harbor, you know, drop a bomb on whatever. It can be anything they want to send, but they can send 2 possible messages because 2 is the largest number that's not trivial. So they can pick 2 messages. And this guy up here, he's going to pick a bit B, either 0 or 1. Because we're computer scientists, we have to make everything 0 indexed, okay? And he's going to encrypt M sub B, which basically means either M0 or M1. We're just flipping a coin, and we're picking one of those 2 messages. Okay, we don't actually want this guy to output the decryption, although it doesn't really matter. What do we want the adversary to do to win this game? Right, we want them to guess which B was picked. So we'll call it their guess B prime, and we'll say that the win condition is B equals B prime. Okay, we're almost there. We have a little problem. Let's say that I'm an adversary, and my strategy is literally, I don't have any decryption chops. I can't decrypt these messages. Like, I'm faking it. What's my strategy? What am I going to do? And how often am I going to win? Yes?
You could randomly guess.
Right. So there's always a dummy adversary, a dumb adversary who just flips its own coin and says, okay, B prime is 1, or B prime is 0. How often is that adversary going to win?
Half of the time.
Half the time. Okay, so we don't want the success of this game to be determined by, we can say the adversary's probability of winning is defined as the probability that B is equal to B prime, but that's not what's interesting to us. What we actually are interested in is a different term. Okay? We'll call this the advantage of the adversary. Okay, so the advantage of A is equal to this minus the dummy adversary, 1/2, and we'll put absolute around it just to make sure. So it could be less than, it could be more than. Okay? So the adversary's advantage in winning this experiment is defined as the probability that he guesses right minus 1/2. So the difference between 1/2. So if the adversary always guesses right, then his advantage would be 1/2 because it would be 1 minus 1/2. Does this make intuitive sense to you? Yeah.
Is the second term in that difference, will that change if your message space grows?
No. In fact, your message space, we haven't even defined what the encryption scheme, let's assume it can take messages. By the way, one thing I haven't specified. Let's assume that the encryption scheme takes messages of arbitrary length, but, and this is a key thing, these guys are of the same length.
So, I'm sorry, I meant if the message space grew, like if there were 3 possible messages.
Oh, yeah, it would.
Right.
But we never need to worry about 3 possible messages because it turns out that this game with just 2 possible messages is general enough that there's never a need to have a 3-message version of it. Okay? So this is it. So if we have this particular game, now we basically have got it to the point where we can say there's an advantage function. And really intuitively, for something to be semantically secure, or IND-CPA, which I'll explain in a second, we want the probability, we want this advantage function to be very small. So we actually will want to make the statement that there exists no adversary that when they play this game with my encryption scheme has an advantage that is negligibly different from 1/2, or that is non-negligible if you want to get into the actual definition. Negligible function, something we'll talk about a little later if you haven't seen this. Just for now, assume that an encryption scheme is secure if this advantage for all possible computationally limited attackers is very small. We haven't quite gotten to the end of this definition yet. Go ahead.
Doesn't that assume that the adversary is kind of like cooperating with the game?
So remember, this is actually a game where the adversary has to cooperate. So give me an example where the adversary cannot cooperate.
Like if they can like determine which message was sent every time, and but they still send back a random result.
So, I mean, you've just defined an adversary who's like got some magical decryption capability, but like whiffs it. So that's okay. That's fine. I mean, let me put it this way. let's say that there is an adversary that can actually answer the game correctly if it cooperated, but for some reason just chooses not to and like sends back a random result. Since we're going to enumerate over every polynomial time adversary, or every adversary, if that guy exists, then there's going to be another adversary that like does cooperate and doesn't with it. So basically we're saying for all adversaries we want this to be small. Yeah.
But if the message 0 is the same as the message 1,
What happens then? Does that help the adversary?
I mean, things, so even if that is so it's like there's no difference.
Yeah, you're giving me another case where the adversary might be able to win, but for some reason has like blown their own foot off, right? Because if the adversary sends m0 equals m1, then there's literally nothing they can get that will help them win. Like they're reduced. Their maximum possible advantage will always be 1/2, because they're always going to get the encryption of the same message. Like there's nothing in this that would tell them what B was. So again, there's lots of things the adversary can do that will like mess them up. They could like refuse to give B prime. Like, I hate this game, I'm not playing. But that doesn't even help them, because like we could just say, okay, if they don't give an answer, we'll just always assume their answer is 0 or something. Like, you know, there are always these kind of pathological cases, but like these don't help. None of these help the adversary. They're just the adversary kind of trying to mess things up. So we're going to say that we want the advantage for this for an encryption scheme to always be small. But we're not quite done. We need to give the adversary one more push. And it's down here, this part. So I said, even if the adversary can request chosen plaintexts, meaning they can ask for the encryption of any message they want, they still shouldn't be able to win this game. How do we modify this game to let them ask for the encryption of chosen plaintext? What would you add to this terrible diagram I built here? It's just a game. We're just playing a game. What do I add to it? Yes?
Like a loop, say, hey, I can do this as many times as I want.
Yeah, okay, where? Well, let's not add a loop for this stuff. Let's leave this alone. Let's add our loop up a little higher. I'm running out of space. I'm going to move some things. I'm not changing anything, I'm just moving. Squishing this down a little. Okay? All right, so let's say that the first phase of the game, the adversary can send any message. In fact, it can do this adaptively. It can send a message, coming up with, let's call it M. Well, I'm just going to say it can send any message M, and it will get back the encryption. I mentioned there was a key here. Under K, oops, I'm drawing that wrong. The encryption under K of the message it sent in. That's it. We're just going to let it do this, and we're going to let it repeat this, like you said, in a loop, as many times as it wants. When it's done, it can say, okay, I'm done. I'm done. Ready to go on to the next step of the game. Now here's my M0. Here's my M1. Send me a challenge, and I'll try to guess what it is. Okay, so all we're doing is adding on this first phase where it can encrypt. So if we're playing poker, right, the first thing it's going to do is encrypt all 52 cards. This M, by the way, this is not the same M each time. It can pick a different M. So it's going to encrypt all the cards from 0 to 51, get their ciphertexts, and now it knows the encryption of all those poker cards. What's it going to do next? Well, how do you win this game? Yes.
Well, we have to make sure M is not equal to M0 or M1.
Why?
Because then you can just send M0, M1, record the result, and then see what comes back.
Why is that not a valid strategy for the adversary? Explain. What would happen? You're right. You're right. So you're thinking, if we use something like a block cipher, right? There's an attack. It's not going to satisfy this definition. Something bad's going to happen. Because the adversary is going to get the encryption of M0. It's going to pick some M0. It's going to get the encryption of it. Wham! It knows that encryption. Deterministic algorithm, so it's always going to be the same encryption for M0. It's going to send in M1. It's going to get the encryption of M1. Now it knows it. It's built a little dictionary of these two things. Now it's going to send in, okay, I want to challenge you on M0 and M1. And it's going to get back the encryption of one of those two things. And what's its strategy? Well, it just looks. It has a little dictionary of ciphertext. It says, okay, if this matches, the M0 ciphertext, I know it's 0. And if it matches the M1 ciphertext, I know it's 1. So if we used a block cipher, just a block cipher, and we tried to win this game, or we tried to see if it satisfies this definition, does there exist an adversary that succeeds with probability or with advantage greater than something tiny? Right. In fact, the adversary against the block cipher, there is an adversary that wins 100% of the time. So their advantage is 1/2. Yes?
When your key space is large enough, if your key space is large enough, you can't memorize everything. And then
It doesn't matter because, no, I mean, this doesn't require key space. The key space is irrelevant. We did pick a key here.
I'm sorry, not key space, but value space.
Sure, but remember, your value space is 2 messages. So we are actually saying that in this game, your challenge space, you get to reduce the space of all possible ciphertext just down to telling the difference between the encryption of these 2 messages, and you get to choose them. So it's really an indistinguishability game between 2 messages, and on top of that, you get to ask for the encryption of both of those messages beforehand. Okay, so one of the things that's so interesting about this game is that algorithms like ECB mode, which is just using a block cipher by itself, don't satisfy this game. They become broken instantly the minute you try to throw them in there. In fact, turns out any non-randomized encryption scheme fails this test because there's always an adversary who does exactly this strategy. They ask for the encryption of both sides plain text, and then they can instantly win. So what do we need to do to make this work? How do we make an encryption scheme that can actually meet this crazy strong definition of semantic security? 2 people back there, but how about the first one? Closer one. Yes, you. Yes, were you raising your hand?
Yeah, have it change each time you like send a message,
What do you mean change? Have what change?
like the encryption. So
Good.
the same message twice is different.
Very good. So we have to make the encryption algorithm to satisfy this definition. We have to make the encryption algorithm randomized. If it's deterministic, it can never be semantically secure. Doesn't mean that every randomized encryption algorithm is itself semantically secure. It's just, like I said, table stakes. You need to have randomness in this in order for it to work. And the reason is, if you have a randomized encryption scheme, let's see if this attack works, right? So your attack was to send the M0 message and get back the encryption of M0, and send the M1 message and get back the encryption of M1, and then do the challenge and compare it here. But at least, hypothetically speaking, if there's some randomness that goes into the encryption algorithm, now there's at least a possibility that the message you get back here when you sample an M0 or when you encrypt M0 will be different than the ciphertext you'd get here if this was M0, because there's now randomness pushed into that algorithm. So there's a chance it might break your attack. So deterministic can never be semantically secure. Randomized might be, yes.
For this whole example, are we assuming that the encryption is public knowledge and it's just the key that's private?
Yes, and remember, this was one of the things we demanded at the beginning of this class, is that all of our algorithms are known. Encryption, the encipherment or encryption algorithm is fully known. Decipherment, decryption, fully known. The adversary can have all that information, but the key is the only thing that I kind of, my terrible little diagram up here, is the only thing that was picked and not given to the adversary, right? So this is kind of the one exception. Any other questions?
So does that mean that even if it lands in a pseudo-random or generator, it's still not semantically secure? And then, right? Because
if you're saying, basically, if the ciphertext is deterministically based on the plain text, it is not, right? Because that's not really random, right? If it's always going to be the same ciphertext for a given plain text, you're toast. Because then the attack is just get the encryption of both plain texts, run this thing, compare. You always win. Pseudo-random doesn't help.
How does the decipher get the random information?
Good question. Good question. Okay, so how does the decipherer get rid of it? Well, I mean, we'll get to that. We'll get to some actual schemes that are randomized in just a second. I'll show you what happens. All right. Okay, so I wanted to show you, and I'll post the slides. I didn't want to use this diagram because not that it's actually much better to have a squinched little diagram up there, but this is a picture of the same thing. It'll be in the slides that I post. Yes.
Is there supposed to be an implicit third player in this game who has the key and is able to decipher? Because you can think of the challenger as you just randomly scramble.
Oh, you're saying could the challenger like be a cheater?
Right. It's randomly scrambled with and nobody can get that.
Yeah, no. We require the challenger is honest. So this is an experiment. Like if I let you play with like a dishonest challenger, that would be bad. So the adversary can do whatever they want. But the whole point of the game is the challenger actually sticks to what he's supposed to do. He's not going to cheat you. because otherwise meaningless. So that's the assumption. Honest challenger plays with an adversary. The definition of adversary is like, he can do anything. We can't restrict what he's going to do. We just assume that he's going to try to answer us. And, if he doesn't answer us, we don't even care. But if he gives us an answer, all we care about is that he does not win with anything but like negligible or small probability. All right. Yes.
I just want to make sure the key in the first step is different from the second step.
No, same key. Sorry, the key is chosen by the challenger at the beginning of the game. It's a different key every time you play the game. And it stays the same throughout the entire thing, all the way to the end. Okay, the next time I play the game, obviously maybe a different key, but for the entire game, one key picked appropriately by the challenger. Right? So if it's an AES key, they pick a 128-bit random AES key, and then they play the game. So it's fixed, but it's chosen at the beginning. And the adversary obviously doesn't know it, or it would be toast. Or it would win. Okay, so what I just tried to convince you of, and I keep using the word ECB, by the way. I don't know if I've said what ECB stands for. Can anyone remind me? Maybe I talked about it last time, but didn't define it today. Good, okay. Electronic codebook mode sounds fancy. All it means is you're using the block cipher in exactly the obvious way you'd expect to use a block cipher, right? So in the olden days, spies used to talk about code books, which were books that had like all these plain texts and lists of codes they would translate into. And when they invented block ciphers, someone said, this is like an electronic code book. Has lots of, it's an algorithm that combines all that stuff. So using the block cipher in the way it was intended to, or that looks like it should be used, is called electronic codebook mode. And we say that it's not semantically secure because it's not randomized, and therefore there's an attacker who's going to always win this game. It's not semantically secure. So we have to do something with the block cipher to make it into a randomized encryption scheme. And the thing we do with it is called a mode of operation, other than ECB mode. So there are a handful of these. I'm going to talk about a couple. One is called cipher block chaining. One is called counter mode. And there are cipher feedback mode, and so on. And so these actually do a couple of really useful things in one go. So the first thing they do, second thing really in this list, is they add randomness to the encryption process. So at the time you encrypt a message, you sample some random stuff from a real random number generator, and you pour it into the encryption, and now you don't get the same ciphertext back, even if you encrypt the same plaintext multiple times. One. The second thing they do that's actually really nice is they solve our other ugly problem with block ciphers, which was tux. Right? You have long messages, we're enciphering them with ECB mode, it leaks patterns through. And so what they do is they do stuff to link together those blocks of encipherment so that you don't have pattern leakage. And they do this all in one go. I'm going to show you a couple. This is a lovely diagram you can find on Wikipedia. Let me see if I can redraw it. Okay, so the first one. All of these modes of operation work with basically any block cipher. And so you remember a block cipher is an encryption algorithm, an encipherment algorithm, and a decipherment algorithm. And it takes in a key and a plain text. That's the ingredient that we need. I'll just go with this. All right. So CBC mode starts out, well, maybe I will draw. Starts out with a value that is called an initialization vector, or an IV. Okay, this is the randomness that goes into the encryption. How long is the initialization vector going to be? Well, it depends on the block cipher you're using. It is the same length as one block of input. Let's go with AES just for these examples because it's 128 bits and I can remember that easily off the top of my head. So if we're going to do CBC mode with AES, we'll pick a 128-bit random initialization vector each time somebody asks us to encrypt a message. First step. Okay, now we're going to take that IV and we're going to take our first block, meaning the first 128 bits, of the plain text message to be encrypted, and we're going to XOR this plain text thing with the initialization vector. And we're going to then take that output and shove it into the encipherment mode of the block cipher, along with the key K that we picked. And the result of that, we're going to call that C1, meaning the first block of ciphertext output. And then we repeat. Okay, so let's say we have P2 up here, the next block we want to encipher of tux. No problem. We're going to take that and we're going to shove it into XOR with something. Well, what's the something we use? We don't want to use the IV over again. We want to use something else. Turns out we can actually take the ciphertext output we produced in the first block, and we feed that forward into the XOR with the next plaintext block. And then we take the results of that, and we shove it into the encipherment, again, with the same key, K, going into that, and so on. And that gives us C2. We continue this process for P3. And I'm not going to keep drawing, but you can look at that. Okay. So this is cipher, CBC, ciphertext, cipher block chaining. And you can see why it's called cipher block chaining, because you're building a chain by repeatedly feeding outputs of this encipherment into the next function or the next iteration of this thing. And you can keep going for many, 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 many blocks.
Is it the same plaintext?
What's that?
Is it the same plaintext?
What you mean, sorry, P1, P2, and P3?
Yeah.
I'm assuming that we've taken our message, and broken it up into 128-bit chunks.
Oh, okay.
So P1 is the first 128 bits of the message. P2 is the next 128 bits. P3 is the next 128 bits. Actually, it's a good question. What if the message is not a multiple of 128 bits? What are you going to do?
Just one chain?
What's that?
Is it just one chain?
Well, I mean, just one chain. What do you mean?
Like just one? Because you did it 3 times.
Oh yeah, I'm assuming that my message is at least 3 blocks long.
Yeah, so if it was just one, it's just going to be.
Oh yeah, you just do one. But what if my message is 3.6 blocks long? Padding. Okay, so good. So we're going to assume that if you have a longer message, maybe P3 needs to be padded, but that's not really a cryptographic function. You could just add padding in whatever way suits you. And we'll talk about padding later, but that's one way to do it. Yes?
For each C, is that considered one round?
I don't know about the word round. I don't like that because there's rounds and lots of things. But yeah, call it a round if you want. It's one iteration of CBC mode. Good. All right. So one of the things you notice about this, and this is just intuitive, it's not some kind of security proof, but because IV is random and chosen differently for each message, you get some kind of randomness in here. So remember, we talked about the one-time pad. Essentially what we're doing here is a one-time pad encryption of this first block, P1. So we're one-time pad encrypting that, and we're feeding it to the encipherment. And that, we believe, should affect the value of C1. And the idea here is that this will feed forward or feed into the next block and so on. So that randomness will ultimately chain forward to every block of the message. Yes?
Is the initialization vector something you have to keep secret?
Good question. Let's ask, how do you decrypt a CBC mode ciphertext? So I've given you C1, C2, C3, and you have the key. How do you decrypt it? Give me steps. Don't look at this. How do you decrypt it? Like from my diagram over here. Good. Okay, so I take C1 and I run it backwards. This time I won't use E, I'll use the decipher mode of the cipher, but that's all one block ciphers. So I'll go back to here, I get here, and how do I get back to P1 from here?
You XOR out the.
Good, so I XOR whatever I get out of this thing with the IV to get P1. So we know that's invertible. Okay, so I do need the initialization vector in order to decipher, and I'm going to answer your question in a second. But we need the IV to decipher. And then if I want to decipher or decrypt C2, well, I just do the same thing. I get to here, and it turns out I don't use the IV. I use the previous block of ciphertext output, but then I can get P2 and so on. Yeah.
So you only need the IV for decrypting the first block.
Correct. Correct. That's right. So you need the IV, and then you can think of this as we're using the ciphertext blocks kind of as the IV, the virtual IV for the next iteration, and so on. Okay, somebody.
How is it more secure than UCP if, let's say, the adversary is willing to just give up the first block?
Well, what do you mean by the adversary is willing to give up the first block?
So if the adversary is willing to say, I don't care about what the first block is talking about, they can decrypt everything.
Well, so here's the thing, right? So you've got the intuition that the first block of this is randomized because we've XORed the IV into the plaintext. But this randomization continues through because this randomization goes into this first plaintext block, and that gets enciphered, and it actually then goes to C1, and C1 now gets fed forward into the next round. And so if I were to change this IV here, and you can do this experiment later in the class, you'll find that every single ciphertext block throughout the entire message will change. And will change in a very random, unpredictable way. Trust me on that for now. It does. We can talk about why it works later. It just does work. Okay, last thing, and I know I gotta let you go in 1 minute. So somebody asked me, should the IV be kept secret? Somebody give me an argument for why the IV should be kept secret.
I think it must be secret, otherwise you can use all the other.
You break the whole thing.
But you don't have the key, right? Let's say that I'm going to give the IV out. I'm going to ship the IV in clear text along with the message. So my resulting thing that I send over the wire is going to be all this stuff. How is the adversary going to break the message, assuming the adversary doesn't have the key? Yeah.
They can just try and cycle through all the various IV combinations and send the same message, so they can build like a
How does so? Are we assuming the adversary is doing a chosen plain text attack, or are they trying to decrypt?
I guess I was thinking of doing like the game we were playing before.
So in the game that I was playing before, in the semantic security game, you're saying that, right, so you're saying that they could choose the IV, which would be really bad. You're absolutely right. So the one thing that we're going to specify, and maybe I didn't make this totally clear, is that the IV is chosen as part of the encryption process by the person who is encrypting the message. It's chosen randomly. If the adversary gets to pick the IV, really bad stuff happens. It's not randomized anymore. If the person who's honest, who's encrypting the message, picks the IV and they pick it randomly, then your attack won't work because now the adversary doesn't have control over it. We'll talk more about this on Monday. One last question, shoot.
Doesn't this rely on the decryptor receiving every single message in the correct order?
Only from when we talk about a message consists of the IV for this thing and all of the blocks of that message. So they have to get that. If they miss some of it, yes, you're right. They will not be able to continue decrypting. But it's not like every message. Like if I send you a 10-block message and you miss some of it, you just lose that message. If I send you like another message later on, you'd be able to decrypt that. So that's the point. All right, sorry, we gotta pick up on